Good afternoon or good morning, depending on where you're at. Welcome to the, what month is it? September ASBI webinar. Your moderator today is myself, Wade Bonzen. I'm chair of the ASBI Construction Committee, and I'm a project development manager for complex bridges with GM2 Associates. Today's presentation is called Engineering the West White Rose Concrete Gravity Structure, Design and Construction Insights. And we'll get into that here in a few minutes, but first, a few announcements. Mark your calendars. Coming up here very soon, in about a month or so, is the 2025 ASBI Convention and Committee Meetings. It's going to be held in Bellevue, Washington at the Hyatt Regency from October 26th through the 30th. The technical program is the 27th through the 29th, and then prior to that, ASBI will be holding a series of committee meetings on the 26th and 27th. And then following the convention's technical program will be a series of PTI and ASBI committee meetings on the 29th and 30th. Just a reminder, the room block cutoff date is October 3rd. That's coming up very quickly next week. So make sure if you're attending to register and book your room now to get the ASBI group rate. Another reminder, our monthly webinars are typically held on the last Wednesday of each month at 1:00 p.m. Eastern time, although sometimes they do move around a bit. Recordings of all the past webinars are available at the ASBI website under the Learn menu. And you can pre-register for all the ASBI webinars for the whole year using the QR code that's on the screen now, or the link at the bottom of the screen. And this is really convenient because you'll receive an email notice 1 month prior to each webinar. So this is a great way to get these onto your calendar with very little effort, and you'll be notified as they come up. The October webinar is going to be held in conjunction with the National Concrete Bridge Council, and it is going to be an introduction to concrete segmental bridges presented by Eric Johnson. That'll be October 22nd at 1:00 p.m. Eastern time. Our project today is not a bridge, but if you do want to learn more about construction practices for concrete segmental and cable stayed bridges, you can always download the Construction Practices Handbook. This is a free document available for download from the ASBI website at the QR code below, or you can go to the Publications tab on the ASBI website. And just as a reminder, we have an expanded scope at ASBI that the Board of Directors voted on about 1.5 years ago, actually almost 2 years ago now, to work collaboratively to advance, promote, and innovate concrete segmental bridges and complex concrete structure technologies. Our speakers today will certainly be filling us in on that topic, so we're looking forward to that. A few instructions for the webinar, just some housekeeping here. If you lose your connection, you can rejoin the webinar in progress with the link that you were provided. But unfortunately, this is a live presentation, so you'll miss a little bit of that content while you're away. PDH certificates for attendance will be issued to those folks who are meeting the minimum time required in the session. And just a pointer there, if you're watching this on your desktop, I would recommend keeping the window with the presentation in it your active window as much as you possibly can. That's how GoToWebinar counts your attendance time. Allow about a week for your attendance certificate to arrive via email, and we'll do Q&A at the end of the session. In order to submit questions, you can go to your desktop app at any time for GoToWebinar under the questions box, and you can enter your question where it shows here on the screen. If you're on a mobile device, it's a little bit different. In the upper right-hand corner, there's a question mark, and if you touch that, it'll open up a question box where you can type in your question for our presenters. Our presenters today are Babak Pourazarm. He is a licensed professional engineer in the United States and Canada. serves as a structural engineer and discipline team leader with Arup's South Geography Bridges, Civil and Offshore Structures Group. He's based in Houston and specializes in the design and delivery of major infrastructure projects. And he led Arup's structural team through the concept, detailed design, and construction phases of the West White Rose project concrete gravity structure, which is a complex offshore platform. We also have as a speaker today, Dr. Hossam Alalaily. He's a concrete technical lead and construction manager with AtkinsRéalis and is a construction professional with a focus on concrete materials and field execution. He served as the concrete technical lead on the West White Rose CGS project, where he supported the planning and delivery of concrete construction for really one of Atlantic Canada's largest offshore developments. His work involves addressing durability, marine exposure, and constructability challenges in a demanding environment. So Babak and Hossam, I'm going to turn control over to you, and we'll get going.
Okay, hello everyone. Hopefully you can hear me and have my screen here. Can somebody confirm that if it's possible?
Yep, sounds good. Thanks, Babak.
Okay, great. Very good. Thanks again, everyone. Thanks, Wade, for the introduction. I am Babak Pourazarm, and I'm here with my colleague Hossam to present engineering and construction of the West White Rose concrete gravity substructure. To start with the purpose, the purpose of this is to have a quick look at the practical ways of implementing the project and have and understand some of the strategic decisions that was behind CGS construction. We'll talk about some of the innovative techniques that were used in the construction, and we have some how to address some of the unique engineering and logistical challenges that we had for this offshore construction. As for the agenda, we'll have an overview of the project, and we'll talk about the main design drivers, and have a conversation about construction overview. I will start the first part, and then I will hand to Hossam to discuss some of the construction aspects of the project. The project is located in Newfoundland, or client is Cenovus Energy, a Canadian oil company, and Arup was the main designer and prime consultant on the job. AtkinsRéalis, in collaboration with Dragados and Penacon, were the construction firm of the project. In terms of the location of the project, we are on the eastern point, most eastern point of the continent, and in Newfoundland, and the offshore side is located 350 kilometer offshore Newfoundland in the Grand Banks. The construction site is construction site is in the dry dock in Newfoundland, and the CGS was ballasted down in the nearshore site and then towed offshore. The water depth at the site is about 120 meters at the edge of the Grand Banks. So the West White Rose project is developed in an existing oil field in the Arc Basin. The Cenovus is already having facilities and operations there. They're extracting oil through subsea stations that are connected to a floating operation, floating production, storage, and offloading facility, FPSO. The development of this project is to use the oil reserves of the site more efficiently and have that connected and integrated with the existing facilities on site. It is expected that at operation, they will increase the production by about 45,000 barrels a day. This platform is essentially a fixed wellhead platform. It means that it is permanently installed in place. The CGS, there are two main components there. The foundation, or the CGS, that's shown in gray there, that is a pre-constructed concrete foundation that supports an integrated topside. The topside is where the operation happens, and it has facilities for living quarters, drilling, heli deck, and other safety equipment. And the design of the CGS is such that it just provides a stable base for the environment that the platform is installed in. In terms of the key client needs, they wanted a wellhead platform that allowed efficient drilling and extraction of the oil. That was important because it required a fixed platform for that purpose. They also wanted the platform to be connected to the existing FPSO and subsea centers that they have there. Another key requirement there for this project was that they did not need any storage of the products or any processing of the products on this facility. That led some of the key design decisions on the project, and I will get to that in a bit. In terms of the overall scale of the project, some key dimensions. The facility is 145 meter tall, about 475 feet. The water depth at the site, the offshore site, is 390 feet about depth. The width of the platform is about 400 feet. The total concrete volume is about 100,000 cubic yards for the CGS, and we had about 32,000 tons of reinforcement in there. The completed weight, the total weight of the CGS at completion is about 210,000 tons, and there is an additional about 5,000 tons of structural steel and outfitting inside the CGS. The environment that the CGS is installed in offshore Newfoundland is like I mentioned, around 350 kilometers east of the coast, and there is a harsh environment. We have to deal with very large waves. There is waves as large as 100 feet tall, and the CGS is located in an iceberg alley, so it is exposed to contact from iceberg in that location. There is the exposure to ice itself, and the management of the ice impact risk is provide some opportunities and risks to the strategies of designing the CGS that I will be talking about here. The active management there is that the icebergs basically float from float down to the area, and there is a number of operators of the oil fields that manage the icebergs and tow them out of the way. The one important aspect of this platform that we are designing is that it is designed, because there is no oil storage in the facility, it can be designed with the exposure class L2, which means that the facility is designed to be manned but evacuated in the case of an iceberg impact. Other similar facilities in Newfoundland, Hebron, and Hibernia, two other CGSs there, are designed for L1 exposure class, which means that the return period of the iceberg load is for those facilities in 10,000 years, while for White Rose is 1,000 years as an L2 exposure. There is icebergs can come in all sizes and shapes, and this is a key aspect of CGS design. It allowed some main features of the design that we had for our CGS. In terms of the form of the foundation, there are two key types of offshore foundations, being jackets and concrete gravity structures. Jackets are very good for dealing with the wave loading because of the relatively small area exposure to the wave load, but CGS have bigger exposed area and have more wave loading on them. But jackets are more vulnerable when it comes to ice loading. And I don't know why these slides are jumping on me. Apologies. So CGS was selected for the environment that we have to have sufficient protection of the drilling conductors against iceberg loading. Two main methods of CGS construction. One is dry build. The one on the left here is White Rose CGS that is dry build, and the one on the right is Hebron, which is a dry wet build process. For the dry wet structures, the first part of the construction happens in the dry dock, and then when there is a sufficient progress, the dry dock is flooded and the partially built structure is towed to a deep site, and the rest of the construction happened in a deep water floating condition. And that means that as the structure is built, that the draft is constantly changing. While for the dry build CGSs, all of the construction happens in dry. It provides a lot more control over the quality of construction. It's a lot in terms of logistic, more efficient to build the structure, and potentially faster and higher quality construction can be accomplished in dry build. One note is that when we have the structure as dry build, the opportunity to test the structure for leak tightness is limited, while when a dry well build approach is used, that automatically happens during construction for the trade-off of cost. So this is an aerial view of the dry dock for White Rose project. This is a purpose-built dry dock off the coast of Newfoundland. As I mentioned, all of the CGS construction was completed in the dry dock, and in terms of efficiency of the construction, it was a great choice to streamline the schedule and avoid potential delays that could be associated with the floating phases. It provided a safer environment to work for the equipment and for the personnel there to not have to work in a deep site. The main construction of the CGS, so the next few slides, I'll explain the main kind of design life stages of the CGS, and before we move into what the key design drivers are. The CGS was built in the dry dock, and the main vertical elements of the CGS were slip form. The slip forming method was beneficial to minimize the number of construction joints, which is important for the leak tightness of the facility, and a lot of these elements are curved shape for dealing with hydrostatic loading that the structure sees during offshore tow and installation. After completion of the construction, the graving dock is flooded, and the CGS is designed to have sufficient underkeel clearance so it can be towed out of the graving dock and transported to the nearshore site. Nearshore site is a sheltered deep water location near the site where solid ballast, about 100,000 tons of solid ballast added to the perimeter cells of the CGS to increase the draft of the structure for the offshore tow. Then there is an arrangement of the vessels. There is 3 leading vessels and 1 control vessels on the back that then towed the CGS that was floating at 65-meter draft. The water line is at the shaft, as you can see, and the entire caisson is under the water line. In this condition, the CGS was towed 350 kilometers offshore and installed in position. This is showing the CGS after installation. The lowering of the CGS was done through adding water ballast inside the caisson cells and in the shaft. CGS is then placed on a prepared seabed of about 500 discrete gravel mounds that were placed on site before CGS was installed. And I would say that it was a great work by project contractors to control the CGS during lowering, and it was positioned about 6 inch to the target position of the structure, which was a great achievement. After CGS is in place, then the top side, which is constructed in Ingleside Cubit Yard, was towed from Texas to Newfoundland on a transport vessel, and a special vessel, this vessel you see on the picture here, it's called Pioneering Spirit, was used to install the topside on top of the CGS. Just a little about this vessel. This is world's largest construction vessel. It's designed for a single lift installation and decommissioning of platforms, large offshore platforms, and it provides significant efficiency in the offshore process of installation. When the topside is installed, then there is a floatel, basically, which is a supporting vessel is floated to the side and can get connected to the CGS, and that provides accommodation for the personnel who are involved in commissioning the structure. This condition that you see here is more or less where we are now. Some of the commissioning work is still ongoing. In terms of key design drivers, what the CGS is essentially a pre-constructed foundation that is stable under self-weight. It is sitting on the seabed, a prepared seabed, and the frictional resistance between the sliding resistance is provided through friction between the CGS and the gravel bed there. And there is sufficient weight and solid due to the weight, self-weight of the CGS and solid ballast to make the structure stable in that condition. The general philosophy of design, there is, I think, one important philosophy here, which is the CGS needs to be strong enough to deal with the installation and operation forces. At the same time, it needs to be light enough so it can float out of the graving dock with sufficient under clearance and also be stable during offshore tow and installation. This meant that a lot of the CGS elements need to be optimized for their weight. So we have many elements that are curved in their geometry, many elements that have a high ratio of reinforcement to thickness. And we had rebar densities up to 525 pounds per cubic yard in some of the dense areas of the CGS. But overall, it was a high density of reinforcement in the structure. That very dense reinforcement meant a very specific planning of the rebar detailing and 3D reinforcement model and BIM development. The shaft of the CGS is post-tensioned to handle the overturning loads that come down from the environment and topside. And we also, like I mentioned, had a design to minimize number of construction joints. That meant that we used larger slip forms to build main parts of the structure. Shaft design generally is governed and under global overturning by wave loading. There's major wave loading on the shaft. The icebergs and contact from ice and potentially from the vessels have governing conditions that are local to the shaft. For the vertical post-tensioning is provided to resist the overturning. And at the very top of the shaft, where the topside legs come down, we have horizontal post-tensioning to deal with loading from the topside. The caisson design, because we didn't have storage, generally this caisson comparing to other CGSs in the area is smaller because we don't have the storage, and we had the dry build construction. We did not need to have the caisson watertight during operation. Water tightness was required during installation to make sure that there is no significant leakage, but in operation, because there is no storage, there was no need for water tightness, and the structure is designed for the L2 exposure. There are many different critical loading during the design life of the CGS, from the tow to installation. There is about, at the maximum draft before touchdown, the CGS sees something in the order of 1.2 MPa of hydrostatic load. And during operation, the CGS is designed for major environmental loads and contacts from icebergs and other supporting vessels. The solution overall is a balance between selection of the material and structural form. One thing to note is most of the elements of the CGS that are directly exposed to hydrostatic load are curved, and that generates a good geometry to deal with hydrostatic loads. The rest of them, the interior elements, the radial walls you see in this cut view, are flat elements for ease of construction. I don't want to get into details. There is a lot of detail and engineering, analysis, and design that we have to do to deal with complex stress fields. For example, at the base of the shaft, we had narrow shell elements subject to complex and high level of forces that needed to be considered in design for their stability. direct vessel impact and iceberg impact are other conditions that we had to assess. So we had to use a lot of advanced analysis to address those, and also interaction of the CGS during offshore tow with waves and the CFD analysis that need to be done. There is a range of things that we could be talking about here, but for the sake of time, I think we'll leave the details for hopefully another opportunity. Another aspect of the design that I'd like to highlight before I hand to Hossam for construction of the CGS is the concrete mix. The concrete density is a 60 MPa mix, which is about 9 KSI of strength. But the density of the concrete is modified to be around 134 pounds per cubic foot, and that was important because we wanted to be in a range where the structure is light enough for weight control purposes, but we didn't want to fall into the lightweight concrete range because that will have consequences on the rebar detailing and development and so on. And Hossam can talk about the mix design and how that is achieved during construction. Like I said, the geometry of the elements, the exposed elements to hydrostatic were single curvature or double curvature shells and domes, and those were important to achieve an efficient design and control the weight. And where we could, we went with the planar elements for the slip forming purposes. I think I can hand to you, Hossam, at this point for construction overview.
Well, thanks, Babak, and good morning, good afternoon, good evening, everyone, depending on your location. My name is Alalaily. I'm the concrete technical lead. I'll be presenting the second chapter of the CGS, which is the construction. I would like to thank you all for attending today, and thanks, Wade, for the introduction. And I hope that webinar brings some new insights and add some real value for your technical knowledge. So let's dive in. So for the construction, of such a colossal structure, we have to break down the structure into smaller elements to be able to manage it and construct it more effectively and efficiently. So as Babak said, like the structure was designed in a lot of curved, and that means a lot of challenge for the construction team. So the structure was divided into 4 quadrants and 1 toroid. So that's the 6 vertical elements and the shaft. And then we have horizontal elements, which is the base slab, the roof shells, and the lower dome, and some ring beams. So that's how we have divided the structure into some elements that we can manage easier. So I have a time lapse that we can comment on as we are speaking. So if I can get out of that, Babak, can you help me with that so we can?
Sure, just a second.
Open the video. Yeah, sure. Thanks. So this is a video for a time lapse during the construction for the CGS.
This is paused.
So you can see here that during the construction of the base slab, I'm not sure if it's cutting or what's going on. I'll stop and let you lead that, Babak, if you can, please.
Do you want me to play it?
Yes, please. Yeah.
Okay.
So this is the first phase that we have done, is that we have completed the toroid, which is the center shaft. So you can see here we use the slip form. So the construction of the CGS was done by having 6 slip forms. And the first slip of the toroid was 45 meters, which is 147 foot, and installing rebar, PT ducts, and all the embeds was during the slip form itself, followed by 4 slip form quadrants. The video is, I guess, is like very bad, but we had incorporated the actual video in the webinar, so you guys can watch it in your own time. So the concrete was pumped to hoppers. So if I can pause in one of those video up here, you can see 5 hoppers up top, and then it was done by distributed by buggies to a concrete chute, and from the concrete chute was to forms. The reason for this is that we need to control the concrete going in the forms and have a constant, steady set times for all the concrete as we're slipping, so that we maintain the fresh front and we have a constant slip speed with all the slipping. So you can see one of the pictures here, we're installing the PT coil. So one of the challenges in the video, you can see that one of the slip in the quadrant itself, it's split into 2 portions. So one portion stops at the 27, the wall at 27, and then the rest keep going to reach the 45 meter. And then the final one slip that we had was the concrete shaft. So that's, we slipped almost 100 meter. I'll have more discussion on it. So this is some photos for the, and videos for the construction. And then it will be followed by the flooding of the dry dock itself. So that when we had the, I guess the video is not going as intended, Babak, but. So this is a photo for the chute being dumped in the buggy. This is some of our top management team. This is top view for the top of the shaft and some mechanical work during the installation. So everything was happening. The installation, this is the roof. You can see some of the roof was cast in place and some of them were precasted. And this is a photo of the dry dock as being flooded and then being towed by the Olympic Triton vessel to its deep sea location. So I'll stop at that and we get back to the presentation, Babak. Sorry guys for this, but like it seems like the video wasn't cooperating as intended. So back to the presentations. So the construction of CGS, as we said before, was done by having 6 concrete slip forms poured at almost 55,000 meter cubes of concrete, or 72,000 yards. So the concrete was poured on average of 28 days slipping in the small 5 pours, and then followed by the longest pour that we had, which was the conical slip. So the conical slip, we had 70 days continuous concrete pour around the clock, was 1,500 craft involved in it, 197 layers of concrete of a total of 81,000 meter cubes of concrete was poured, and 57,000 concrete buggy movement by hand was done during that period. So that can show how much effort and planning was done to keep the slip going, and it went really good, flawless, to be honest. It was a good achievement for the team. Then followed by the construction methodology for the roof shell. So the roof shell was done by having some precast element and some cast in place, but mostly was the precast element. So the precast, we had our own fabrication yard, and each precast element is almost 70 meter cubes of concrete. So that was done on the ground and then was lifted, as you can see here, and placed on the CGS roof, and then the spacing in between each panel was stitched. So you can see here some rebar details. So all that was, the rebar was detailed so that there was no clashes when we put it to have the joint between the wall and the precast. So that was a lot of detailing and a lot of planning for it. Then followed by the Mammoth SK355, which is one of the largest and biggest land-based crane in the world. It has a capacity of 5,000 tons or 11,000 kips. So it can reach a radius over 767 foot, so over 2 football pitches can be lifted. So I have a funny story about it, to be honest. So one of the family visit, you can see here the beautiful blue sky and everything, but that's not normally how it shows up in Newfoundland, to be honest. So one of the family visits that we had was really foggy, and the senior was going similar to going like the introduction for the Jurassic Park movie, and was watching the dinosaur, like Brachiosaurus dinosaur. So that's how my kids reacted when they first see that crane. To be honest, it's like, oh, this is a Brachiosaurus. You have a dinosaur in the, because it's super duper high. You can see up here like the size of a truck compared to the crane, or the CGS itself compared to the crane itself, was its massive reach. Next is the topic that's close to my heart, and which is the mixed design. So the mixed design has to go through an extensive, rigorous durability testing to meet the specs and withstand the harsh Atlantic environment. And we have to control the workability, density, sit times, air content, stability, and pumping and thermal properties, because some of the sections was like thick, so we have to maintain the thermal gradation and everything as we're slipping. So to optimize the self-weight without compromising the structural integrity itself, the code requirement is that we have to maintain a modified normal weight, which is 2150 kgs or 135 pounds. That was selected as a sweet spot between a normal weight and not getting into the lightweight. So that's one of the restrictions, that if we got in the lightweight, the longer lap splice is going to be required, and that's going to have much complication. So that's why we got to that sweet spot of having not to have a very lightweight and have a modified lightweight mixed design. So one of the main issues with a harsh environment is that we have to maintain the air content and the air stability after pumping. So we did a lot of pumping trials. So we had the long distance, the longest pump we did was almost 550 meters, almost 1,800 foot. And that's equivalent to 650 foot with various pumping rates and pumping pressure. Based on that, we have to modify the aggregate moistures, the slump loss, the aggregate segregation, any plugging, which thank God nothing happened like that, and the air stability and the pump pressure. So I have to keep in mind that we have to keep feeding the slip form with the fresh concrete, and the air itself still holds itself after all that pressure. So that was one of the biggest challenge for the concrete mix design. Moving to the post tension. So that's one of the key structure elements in the design of the CGS, and Babak mentioned it was optimized to have the size and the weight for the structure, and utilizing one of the novel designs, which is one side is going to be passive side, which is a dead end, instead of having a looped or a U-shaped tendon, because the thickness of the walls is still small. So we ended up having a dead end in the bottom. So the concrete head, like the PT head, was fully encased in the walls. So in the structure itself, there was 60 tendons in the center shaft. The bottom tendon was at elevation 27 to 26, so that's 65 foot from the base slab to 85 foot. That's a dead end. And then the top end was at the top. It was one strand going down. So that was at the elevation 145. That's the top of the CGS. So that tendon is almost 130 meters. That's 426 foot of one continuous tendon. So the tendon itself is, each tendon have 31 strands, and each strand is 0.61 of an inch in diameter, and they show up in coils. And there was 60 of them, as you can see up here, and that's located all around the conical shaft. So you can see up here, that's the dead end side. That's have the trumpet, and the tendons comes in with a compression fitting at the end, and the rebar all around it encased in the concrete. So once we installed that was installed during the slip form, all the rebar, everything. So you can imagine how much planning and effort was done into it so that like it comes perfectly. And at the vertical side, the final was installed during the port itself, which is the regular that you guys have all seen, the trumpet, the anchor head, and the rebar for the coil. So the procedure how we install it is by threading. So once we have everything done, the concrete is secured and everything, and then so we have to thread the tendons into the ducts. So the tendons itself show up in a coil, and then we have an uncoiler frame that puts on top. So we place the uncoiler, and then we feed it with a coil, and then the support frame, and then there is a trick or like a method is called equilibrium, which I'll talk into it in a moment. So once we install, you can see that's the compression fitting that fits in the dead zone. So you can see they're all not all aligned in one location and one elevation. This is to make it easy to fit through the duct. Otherwise, you're gonna jam inside the duct. And this is a typical shape of the coil itself, the PT coil. And this is a placement of the frame on top of the CGS and then feeding it with the coiler. So the coiler have the tendons pre-installed. Once we install it, then we feed it or thread it through the duct, through the frame, and then we have the compression fitting. So each one you can see up here has a color code. So the color code itself, we have 2 anchor heads. So we can pull, for example, we can pull the red one and lower the green one so that they're level. So it's a sequential procedure. And then we drop it to the blue line, and then all the colors are aligned, and we can verify that from the top. So that's how we do the equilibrium itself. So that's equilibrium of the strands inside the duct. Once we have all the strands inside the duct equalized, then we have the injection for the passive side. So the anchor head, the passive side is inside, embedded in the concrete up here. You can see the injection ports. So once the strands are flushed in and as needed, then we have we can test it, and we can see that the repetitive procedure by having a camera that's inside, so we can make sure that all the anchors are already aligned and everything is good. Then we injected with a grout. It's a ductile grout that reach around 100 MPa or 14.5 KSI. It can reach that strength in 3 days. So, and that's how we can hold the strands in one side. And then once we have the strength reached, we can do the stressing. So once we have the stressing, so the stressing itself is normal to any job. So we have the tendons, we have the jacks, and we put the jack on the 31 and have to be aligned. Then the stressing sequence as shown up here, it's each one is in opposite side, so we can have till we reach the 60 strands have been stressed. So the stressing force is 6.7 meganewtons, so 670 tons, and the elongation that happened was almost 33 inches elongation. And once we have reached that and everything is signed, we cut off the strands, which is around like 30 to 50 mils from the anchor head, and grab the cap that's been installed. So after that, you can see some photos up here with the jack and the strands being stressed, and you can see the elongation from where it starts and how it ended up. And then we cut off the strands. So for the grouting operation, we have 2 stages because it's almost 400 foot from where the strand starts till the top of the structure. So the the two stages was we divided the structure into stage 1, which is the 20 to 26 meter. That's where the strand starts, to the 82 meter or the 200-foot injection from the grouting. And then stage 2 is from the 82 mark to 140, which is the top of the structure. So that was done in one shot, stage 1, and then there is another pump with a grout equipment on the second deck up here to get the stage 2. So this is the arrangement for the deck and the grouting equipment and materials. So, and this is finally, this is the All-Star Pioneer spirit that's used to install the top site to the CGS. This is a quick video for it. So how the installation happened. Do you want to, so you can see it was one lift, one shot to install the deck casting. That's the 4 corners, and that's where the top site is going to be sitting on top. We sent the link, YouTube link, so you can guys watch it at your own, because you can see up here the videos is not cooperating that much. So that once it's installed, the jacking is lifted, and then the Pioneer Spirit just leave the structure, and that's all stable, and then all the welding and all the structure happens. So SDP was only responsible for the construction of the CGS, not with any of the towing or any of that. Just like just want to mention that. So that's it for my part. I hope you guys had some new knowledge, or we helped to get some information for you guys. So I guess we have another 10 minutes or so to have some questions.
Yeah, we'll do some Q&A here. We've got a number of questions that folks have submitted. Gentlemen, thank you. That is a absolutely amazing structure. That is definitely not something you see every day.
No, we were so lucky to have that, to be honest, to be part of that project.
Yeah.
Very impressive. All right, so quite a few questions coming in. Great question. Is the structure intended to be refloated and removed at the end of its service life?
I can answer that. Yes, the same way that it's installed, it can be refloated and decommissioned. That's one of the design conditions for us.
Wow, interesting. What are the challenges? Some of the challenges that you encountered during the vertical post-tensioning operations?
So before we did a lot of trials. And for the grouting, for example, how we maintain the grout, to show that the AF anchor grout at the dead end itself is reach the strength. So strength, the grout mainly was one of the things, and then the procedure for the unloading, the 130 meter from the top to all the way down. The first couple was a little bit slower than the rest. So we as we are progressing through the first installation for the first couple strands, we have some lesson learned from it on how we can control the descent, how we can control the speed, and how we can make sure that the compression fitting at the end is equalized. So there was a little bit of lesson learned in the first few, and then after that it was like business as usual.
So how thick were the walls of that vertical stem where the tendons were running through?
1.2 meters.
1.2 meters. Okay, so you had, and were the tendons like basically in, within the middle of that wall section, or were they sort of moved towards the outside or the inside?
As far as I know, it was in the middle.
Yeah. Okay, so you had a lot of cover concrete basically to protect for corrosion.
That is correct.
Yes. Yeah.
Okay. Because as I was watching that, I wondered if you all had considered using individually coated strands, like maybe epoxy coated strands or something like that, to enhance the corrosion protection. But it doesn't sound like you really needed it with that much cover.
That's right. Yep. Yeah, there's only single layer of post-tensioning at the centroid of the section, and the shaft wall is 1.2 meter thick. That's the part directly exposed, and yeah, there's sufficient cover for corrosion.
Got it. Okay. The grout itself for the tendons, was there anything special about that particular mix, especially for, you know, how tall those runs of continuous grouting were?
So we did a trial that we put the grout tube on top of the crane, and we pumped it. So we passed the 82 meters mark. If you want, I can say the brand. It's not that secret, to be honest. It's
Sure.
Target grout.
Okay.
Yes.
That's great. It's fantastic. And do you know, did you monitor the grout settlement near the top anchor? Like, did you sort of over grout up into a standpipe and then monitor for settlement or shrinkage?
Exactly. We did this, and we did like all the testing and procedure from mud balance, like everything is under pressure. Everything, every grout was tested and verified that there was no settlement or anything like that will appear.
Got it. Okay.
Yeah.
All right. Who was the provider of the slip forming system, and was it an automatic slip form or crane set for climbing?
So it's self-climbing, and it was by GPG Global from Austria.
Okay. So for the concrete mix, what kind of durability requirements did you have? Did you have like a maximum permeability requirement, or, you know, what all did you have there? I mean, you're like sitting in salt water for the life of this thing.
So you just like all the above. So freeze and thaw, chloride permeability, abrasion. So all that it has a requirement, and that mix design met all those requirements.
And what is the service life for the structure?
25 years.
Oh, wow. Interesting. Okay. The gravel bed, you said there was a gravel bed that y'all leveled out to set the base of the CGS on. What was the tolerance for plumbness or flatness for that gravel bed?
So that gravel bed is not a flat surface. It is there is a flat surface at the bottom of it to level the natural seabed slope. But then what the top surface of that are individual gravel mounds that are about 6 meters in diameter, about 1 meter or say 3 feet tall. And those are, there's about 500 of them to cover the footprint of the CGS. The reason for that arrangement is that we wanted to have a seabed preparation that is soft and compliance to the first touch as the CGS is lowered and is still under hydrostatic pressure. And then as the on-bottom weight of the CGS is increased, then that deforms and stiffens up, and it then becomes a stiff base for the CGS that is permeable to handle poor pressure of water in the natural seabed. Yeah, the tolerance there, I think, for the mounds was, I don't remember exactly, but I believe was in the order of 4 inches plus minus 4 inches or so.
Wow. And how do you measure that down at the bottom of the sea floor? Is it like sonar or some kind of a remote sensing?
There was a photogrammetry scan of the seabed that they scanned that, and then they could calculate all the relative differences.
And did you guys have, you know, clay layers and other layers that might consolidate or settle over time, you know, underneath that gravel layer? Did you have to deal with that?
There is a clay layer underneath the gravel layer, and one of the challenges that we had for the design of the foundation was that as the CGS kind of wave loading is happening on the CGS, and the CGS goes through the overturning at the base level, the pore pressure needs to exit to achieve the capacity that we need at the foundation. And if we didn't have that gravel layer at the base, the the pore pressure from the center of the CGS will have to go in the radial direction to exit, and that was too long. So the reason for that layer of gravel is to achieve a vertical, basically a route for the pressure to exit. And yeah, so the natural soil there wasn't good enough for putting a CGS on it directly.
Mm-hmm. And was there a sort of a long-term settlement that you were expecting or observed?
I believe there is some, but I do not remember the magnitudes. I don't know if any of the colleagues on the call here can comment on that.
Okay, that's fine. How long did it take to build the CGS in the dry dock phase?
Go ahead, Hossam.
4 years.
4 years, okay. And then once you got the platform and the CGS out there and installed, how long did it take to install the top section and then finally be basically ready to turn it over to the owner for operations?
I would say that the construction of topside and the CGS were kind of running in parallel, one in Newfoundland, the other in Texas. And topside tow from Texas to the construction of topside took years and the Ingleside. But once it was ready, I think it was about a month or so that a special vessel towed it to Newfoundland and then handed it to this Pioneering Spirit, this specialized crane, offshore crane that we had. But after that was transported to the site, it was a matter of hours when they basically lowered it and have it sit on the CGS. And that's one of the main features of that vessel that made that operation in offshore environment straightforward and less demanding.
And you might have said this, but where in Texas was the topside built?
Ingleside and near Corpus Christi.
Oh, okay, fantastic. Some of our folks that worked on the Harbor Bridge may have seen some of that being built.
That's right. That's right. Both of them were in the skyline of Corpus Christi at the same time.
Excellent. Let's see here. So I know you briefly touched on some of the interesting load cases and things that you used for design of that CGS, but can you talk a little bit more about the analysis methods you use, maybe the software packages and any lessons
absolutely.
you kind of learned?
Yeah, absolutely. I think our main kind of what we call global model of the CGS was a shell model for the whole structure. We used a software, GSA software, which is a tool that we use in Arup to analyze that. We use that to filter through many design conditions and design combinations that we have. We had a model for installation stages, a separate model for operational stages, and looking at all the different loading and interaction of those. A subset of those loads, then we had a verification model for that, which is a more advanced kind of nonlinear model, and we used LS-DYNA for that. We had a combination of nonlinear shell elements or nonlinear solid models, sometimes with explicit rebar modeling in there, to look at the different parts of the CGS. In some areas, the stress distribution was very complex, and we had to go all the way to a verification using a nonlinear solid model and explicit rebar modeling. In some other areas, we could use simpler tools. But it was a collection of different tools and methodologies that we used to address that, to cover the whole basis. But the linear elastic first pass analysis was the shell model that we developed the model for in GSA.
Wow. All right, and just one last question here about the concrete mix. Did you all use a conventional mix or self-consolidating concrete?
So it has a slump at the end. So it doesn't flow, so it's not STC now.
Okay. And was there any use of like sulfate-resistant concrete or anything similar to that to sort of counteract the seawater?
No, we just use regular GU and some SCMs and admixtures.
Okay.
There was no corrosion inhibitor or anything of that. No.
Okay. Interesting. All right. Well, that wraps up our questions for today. I was thinking while y'all were talking that maybe what we can do, if people want to stick around, is we can run those 2 videos native in the GoToWebinar app for folks that want to just stay and watch those 2.
Oh yeah, that'd be great. Yeah.
Yeah. And other than that, we're done with questions and answers. So, Babak, do you want to run those videos one after the other?
Yeah, I'm going to do that. The first one is the construction video. What's happening now? Why is it?
You guys, when you see the video, you can type in your questions also, and then I can answer it for
Does
you.
it play? Do you see the video now?
No, it's just black screen.
Yeah, I just see a black screen.
Just see a black screen. That's interesting. Let me try the other one. I don't know where. It doesn't seem to really behave here. Maybe I stop showing my screen and try. Okay. Do you see it now?
Not much of a video, but whatever.
Um,
Wow, those were great videos. Thank you for sharing those.
yeah, no problem.
All right, well, I think everybody was so stunned that they didn't have any more questions, so.
Yeah, if someone have any questions, you can reach out, guys, or you can have the question now.
Yeah, no, we're good. So appreciate it, guys. Thank you very much. Wonderful presentation, and I hope everybody enjoyed today's webinar. And we'll see you next month with the joint NCBC webinar with Eric Johnson. Thanks, everybody.
Thank you very much. Thanks, everyone.
Thank you so much.
Bye-bye.
Thanks, guys. Thank you.